My dear students, today we are moving to discuss on the topic hyperconjugation in organic chemistry. Hyperconjugation is also known as sigma pi orbital resonance, no bond resonance, Baker-Nathan effect. So we will discuss in detail about all these alternative names also. So before moving to the topic, we must understand certain terms. What is this? This is sigma and this is pi. Okay. When we consider a bond between carbon and a carbon, this covalent bond between carbon and carbon is called sigma bond. Okay. So the electrons involved in it, we call it as sigma electrons. Similarly, when we consider an unsaturated system, a double bond or a triple bond, here one is sigma and what is the other bond, which is called pi bond. The pi bond is formed by the overlap of p orbitals of both the carbon atoms. P orbital means the dumbbell shape. This is the p orbital. The overlap of p orbitals is formed pi bond. This is the case of double bond. When we consider a triple bond, here one is sigma, right? And what these two, these two are called pi bonds. So there are two pi bond is there. Two pi bond, and one sigma bond. How this pi bond is formed? Both the side by side overlap of both the dumbbell part. Okay. The side by side overlap create two pi bonds in triple bond. Okay. So the electrons involved in sigma bond is called sigma electrons and pi bond is called pi electrons. And the next term, what is alpha carbon and alpha hydrogen? This is the representation of alpha carbon, alpha hydrogen. When this is CH3, right? When it is connected to a C double bond C. Okay. So similarly, I will write another example. Okay. So here, what is alpha? An alpha carbon or alpha hydrogen. Let me first explain what is alpha carbon. The carbon atom which is attached or bonded to a functional group which is called alpha carbon. A carbon atom which is attached to a functional group is called alpha carbon. So here this is the functional group. This is the functional group. So the alkene ring, this double bond, this is the functional group. Okay. The connected carbon is this one, CH3. So this carbon is called alpha. Similarly, this is the functional group, the aldehyde group. This is the functional group. And the connected carbon, this is alpha. Okay. So the hydrogen atom which is bonded to alpha carbon is called alpha hydrogen. So this is alpha hydrogen, this is alpha hydrogen, and this is alpha. So in this compound, propene, this is propene, 3 alpha hydrogen atoms are there. Here also 3 alpha hydrogens are there. So these are the important terms. First one is sigma electrons, pi electrons, and alpha carbon and alpha hydrogen. Next term is carbocation. Carbocation. Okay. So you know that a carbocation is a carbon cation positive charge. So what is the specialty? Let's consider this example. CH3, C, CH2 plus. This is a carbocation. So what is the speciality? This can also be represented like this. CH3, C, the bond is having vacant. So a carbocation is a cation where the carbon carrying positive charge and that carbon is possessing a p orbital which is vacant, or a carbon which is a positive charge which carry a vacant p orbital. So this p orbital vacant. Okay, so there is a deficiency of electron, right? So you should remember this. Okay. Similarly, what is a free radical? CH3, CH2 radical, right? Which also represented like this. So the p orbital carried by the carbon which is carrying only one electron, which means partially filled p orbital, right? Partially filled p. So a free radical is a compound or a species or a substituent where a carbon which is carrying a partially filled p orbital. Whereas in a carbocation, a carbon carrying positive charge, which means the carbon is possessing a vacant p orbital. Okay. So these are the things we use to discuss hyperconjugation. Now we move on to discuss hyperconjugation. So let's consider one example. This is a propene. Okay. This is a propene. So a conjugated system, a double bond system. So what is happened in a hyperconjugation? For effecting a hyperconjugation or a compound which favor hyperconjugation, there needs a certain conditions. The first condition is first condition is the compound which possess alpha carbon and alpha carbon hydrogen bond. Alpha carbon hydrogen bond is a mandatory thing. So here alpha carbon is there, alpha hydrogen is there. So three alpha hydrogens are there. So this is the first condition. The second condition, this alpha high carbon, which is there must be a functional group is there. Okay. In the compound which possess double bond or a positive charge center or an odd electron center. Okay. Odd electron center. Okay, let me repeat. These are the conditions. These are the conditions of conditions to favor hyperconjugation. So the compound must contain alpha carbon hydrogen bond or alpha carbon and which must possess alpha hydrogen. Second, the compound which contain a double bond, that is sp2 sp2 hybridized, that is a double bond, positive or positive charge center or odd electron. So these are the conditions. So let's consider this example. This is, so there's a carbon carbon double bond is there. This carbon is sp2 hybridized and this is also sp2 hybridized. This is alpha carbon and there are three alpha hydrogens are there. There is a sigma bond between this alpha carbon and alpha hydrogen, and there are three sigma bond with the carbon and hydrogen, and one sigma bond between carbon carbon, right? So what will going to happen in hyperconjugation? This double bond will shift to here. As a result of that, the sigma electrons between carbon and hydrogen will shift to here, which resulted in a carbon H plus, a double bond here. See, okay. Still there are two alpha hydrogens are there. So one alpha hydrogen is there. So we cannot predict this H plus ion is free to move. We cannot predict this H plus ion is free because because this H plus ion is bonded with the p orbital of this carbon atom. So this electron, this bond will comes to here. As a result of that, what will be the next structure? Okay. And what will be the next structure? This this alpha hydrogen will release its electron towards here, okay, and resulted in another canonical structure. So okay, and what will going to happen finally? So this will come here and this will come here, and C H H and again H, single bond C, double bond C. This original structure where we started. Okay, so we started with a alkene. So alkene is having a double bond and an alpha carbon with the alpha hydrogen is there. But what is happening? This double bond, the p orbital will shift to the p electrons, the pi. The p electrons will shift to the terminal carbon. As a result of that, this carbon is getting a vacant p orbital. So vacant p orbital is there. This is the p orbital getting vacant. Suddenly, the sigma electrons between this carbon and hydrogen, the alpha carbon and hydrogen will move towards here, right? So that's what is represented here. Then becoming a double bond between these two. Okay, and but the hydrogen, the alpha hydrogen, which releases its electrons towards the sigma electrons towards the p orbital, is not free to move because it is bonded with the p orbital. As a result of that, the next alpha hydrogen will release its electron towards, and this chain, this structure continues. These structures are known as hyperconjugative structure. Hyperconjugative structure, and this phenomenon is called hyperconjugation. So we can say it as hyperconjugation is the movement or shifting or delocalization of sigma electrons of alpha carbon hydrogen bond to the adjacent vacant or partially filled p orbital is called hyperconjugation. Let me repeat. Hyperconjugation is the delocalization or shifting of sigma electrons from the carbon, the alpha carbon hydrogen bond to adjacent p orbital or pi orbital which is vacant or partially filled. It's called hyperconjugation. And you may have a doubt that why it is called. Now it is clear why it is called a sigma pi orbital resonance. This hyperconjugation is also called sigma pi orbital resonance because the sigma electrons between alpha carbon and alpha hydrogen is overlapped with the p orbital. Sigma orbital is like this. This get overlap. So the sigma electrons are moved to the adjacent p orbital. That's the reason why it is called hyperconjugation is also known as sigma pi orbital resonance. Okay. So this is the reason. Sigma electrons are moved towards the pi orbital or p orbital of adjacent carbon atom. And why it is called no bond resonance? See, in all this canonical structure, the first one, the second one, and the third one, you can see that there is no covalent bond, no bond between the alpha carbon and the alpha hydrogen atom. Similarly, in the second structure, no bond between alpha carbon and alpha hydrogen atom. In third also. This is the reason why it is called no bond resonance. Because in the canonical structure or hyperconjugative structure, there is no bond between alpha carbon and alpha hydrogen atom. But this hydrogen is not free to move anywhere because it is bonded with that p orbital. Okay, this is the reason why we call hyperconjugation also known as no bond resonance. And the scientists who discovered hyperconjugation, the William Baker and Wilfred Nathan. These are the two scientists who discovered hyperconjugation. So hence hyperconjugation is also called by the name Baker-Nathan effect. Okay. So in MCQ question, maybe they will ask define find the example of Baker-Nathan effect. Same. Hyperconjugation is also called Baker-Nathan effect. So let me repeat. Hyperconjugation is also known as sigma pi orbital resonance, no bond resonance, Baker-Nathan effect. Okay. We have already discussed about alkene, the hyperconjugation in alkene. Okay. So we have discussed about propane in the case. Now we will move on to the second case, carbocation. So here, this is an example of carbocation. Hyperconjugation in carbocation. See, okay, this is an ethyl carbocation, right? So this is the functional group, carbocation, the positive charge carried by the carbon. This is the functional group, and the carbon connected to that functional group is called alpha carbon. So this is the alpha carbon. These are the alpha hydrogens. So three alpha hydrogens is there, one carbocation. What is the specialty of carbocation? We have already discussed. This is having a vacant p orbital, right? The carbon is carrying a vacant p orbital. Hence, what will going to happen? The sigma electrons between alpha carbon and alpha hydrogen will move towards here, right? So the sigma orbital and p orbital, the vacant p orbital will get overlap. Delocalization of sigma electron to pi electrons. So this will result in right. It's not completed. It's again move. This sigma electron will move towards here, and as a result of that, right? Again, what will going to happen? This will come here. Okay, and finally this double bond will come here, resulted in okay. So when we consider a carbocation where hyperconjugation is possible, these are the canonical structure and these are the hyperconjugative structure of a carbocation. Now we discuss the hyperconjugation in free radical cases. So here we will consider an ethyl free radical CH H. Here a free radical is there. What is this free radical means? A p orbital with a one electron. So which means this is vacant, right? So partially filled, partially filled the p orbital, right? So what will happen? First we check whether it has this functional group is connected to a alpha carbon or not. So alpha carbon is there. So this is alpha carbon. Whether alpha hydrogen is there, alpha hydrogen is there. Three alpha hydrogens are there. So whether hyperconjugation is possible? Yes, because free radical is there. Free radical double bond positive charge and alpha carbon and alpha hydrogen. Hyperconjugation is possible. So what will going to happen next? This will come here and this will come here, right? So here also a odd electron will come. Here also an odd electron will come. This odd electron and this odd electron will club together to form what a double bond. So the canonical structure or hyperconjugative structure will become right. And the next is this will come here and this will come here. So see the arrow. The head of the arrow is not full, right? So what will be the structure? And which is again moving. This will come here and this will come here. So H radical double bond CH. And finally, this will come here and this will go there. And C H H and H single bond free. So final structure. So this is the example of hyperconjugation in free radical cases. Types of hyperconjugation. There are three types of hyperconjugation. Three types. The first one is conjugation between sigma CH, the alpha carbon and hydrogen, sigma electron with pi orbital conjugation. This is the first type, that is sigma electron with a pi orbital. First type. And example is alkene. Alkene is the very example, that is double bond. Okay. Or alkane substituted arenes. For example, methyl. That is a toluene. Toluene is a benzene ring, an alkyl group. A methyl group is connected to benzene ring. So there are two types, alkene or alkyl substituted arenes. Both execute hyperconjugation by sigma pi orbital overlap. The second type is sigma electrons of conjugation with a positive charge. That is, example is carbocation. We have already discussed the hyperconjugative structures of carbocation previously. So this is the second type of conjugation. Sigma electrons of alpha carbon and hydrogen with the positive charge in the center. And the third type is sigma electrons of alpha carbon and hydrogen with the odd electron. Okay. So we have already discussed about free radical cases of just before. These are the three types of hyperconjugations possibility. First one is sigma electrons with a pi orbital conjugation. Example is alkene or alkyl substituted arenes. Second is sigma electrons of alpha carbon and hydrogen with the positively charged center, that is carbocations, and sigma electrons of alpha carbon hydrogen with an odd electron, that is a free radical. These are the three types. So we are going to discuss on the exception part of hyperconjugation. The first one is carbanion. Carbanions, whether carbanion exhibit hyperconjugation or not? The answer is no. The reason that, let's consider this example. An alkyl group, a carbanion. Okay, a negative charge is there. What is this negative charge shows? Carbanion is always having sp3 hybridization. Okay, so this can be represented like this. This negative charge means two dot, a lone pair of electrons. So this is the structure of a carbanion. Due to this structure, okay, when an alpha hydrogen atom is there, since if there is an alpha hydrogen atom is there, okay, this is a alpha carbon, these are alpha hydrogens. Let's consider this example. Due to this negative charge and the triangle pyramidal structure, the geometry is not sufficient for a compound to enable hyperconjugative overlap between sigma bond and pi bond. That's also first reason. Second reason, due to the fully filled p orbital, due to the presence of a fully filled p orbital, there is no vacant space for the sigma electrons to pass on to it, to accommodate. There is no vacant space in the p orbital on the carbanion to accommodate sigma electrons. Or in other words, we can say it as the negatively charged or fully filled p orbital repel the accommodation or repel the incoming of sigma electrons, which will hinder the hyperconjugation, the possibility of hyperconjugation in carbanion. Let me repeat. Due to sp3 hybridization, the carbon which carrying negative charge is sp3 hybridized and possess fully filled p orbital, which will repel the incoming of sigma electrons, or in other words, there is no vacant space in the p orbital to accommodate sigma electrons. Hence, carbanions shows no hyperconjugation. No hyperconjugation. Carbanions are not showing hyperconjugation. Okay, this is very important. Why alkynes are not significant or not participated in hyperconjugation? There are certain cases where hyperconjugation is possible in alkanes, provided an additional diene would yield a double bond is required in that particular compound. But in most of the examples, alkanes are not significantly participating in hyperconjugation due to the following reasons. First is high bond order. You all know that alkene where one sigma bond is there and pi of overlap is there. So this is a pi bond, this is a pi bond and a sigma bond, right? So the side wise, the side to side overlap of pi bond create the sigma bond is more stronger and more localized. Due to this triple bond structure, the sigma electrons are more localized and hence not possible or not provided for participating in hyperconjugation due to this high bond order. And the second is limited electron density. This alkanes, this triple bond character is sp hybridized. You all know that this is sp hybridized. Due to sp hybridization, this carbon, this triple bond is carrying high electron negativity. Due to this high electron negativity, due to this high electron negativity, the sigma electrons are also not very easy to participate in hyperconjugation because these sigma electrons are less available to donate or to localize relocalization with the adjacent p orbital. Let me repeat. Due to the high electronegativity of sp hybridized alkynes, these sigma electrons are not very easy to participate in hyperconjugation due to this limited electron density on the sigma electrons. And the third constraint is geometrical constraint. Due to sp hybridization, triple bond is having a linear geometry which restrict the overlap of sigma bond or sigma orbital with the adjacent p orbital. So which will also restrict in participating in hyperconjugation. But when we consider alkenes, where which is more flexible than alkynes, okay, we just brief the concept. Hyperconjugation is the overlap of delocalization of sigma electrons to adjacent p orbital to form a sigma pi bonding. And this is called hyperconjugation. And the very important points to solve MCQ is when the number of alpha hydrogen atom increases, the number of hyperconjugated structure also increases, which in turn increases the stability of compound, which in turn increases the polarity of that compound, and hence the dipole moment also increases. When the stability increases, the heat of hydrogenation decreases. That's reversely proportional. And the bond length also decreases. The number of hydrogen atom, alpha hydrogen atom increases, the bond length also decreases. Remember this case. The total number of canonical structure of a given compound is equal to, if we consider hyperconjugation, number of alpha hydrogen atom plus 1. Okay. Number of canonical structure. Total number of canonical structure is equal to number of alpha hydrogen atom plus 1. You should remember this important point. Let's take this example. Here, which there are 4 examples are there. 4 cases. Which compound is not showing hyperconjugation? That's a question. Which is not showing hyperconjugation? So let's consider first, second, third, and fourth. Which compound is not showing hyperconjugation? The first one is acetaldehyde, or which is also known as ethanol. Second one is allyl or methyl acetylene, which is also called methyl acetylene, a triple bond character. This third one is isobutylene. The fourth one is trifluoroacetaldehyde. Trifluoroacetaldehyde. So here alpha carbon is there and alpha hydrogen is also there. So hyperconjugation is possible. hyperconjugation is possible. Okay, I will tick mark there. In this case, a conjugative system, an alkyne is there, but alkyne is usually not so significant towards hyperconjugation. But here, alpha, a functional group where alpha carbon is connected and alpha hydrogen is also there. So, hyperconjugation is possible here. The question is in which case hyperconjugation is not possible. But here hyperconjugation is possible. Here also alpha carbon and 6 alpha hydrogens are there. In isobutylene, hyperconjugation is possible. Right? And what about this case? Trifluoroacetaldehyde. Here, if hyperconjugation favor, if there is a hyperconjugation exists, this fluorine will get a positive charge, right? This fluorine, the structure will become like this. One of the canonical structure will become like this. Right? This will come here and one of the fluorine will donate to here. Right? So the structure, this will not happen. Do you know why? Because fluorine is very high in electronegativity. So a very high electronegative atom carrying a positive charge is not stable and which is not exist. Hence, this compound trifluoroacetaldehyde does not show hyperconjugation because fluorine does not bear positive charge, does not carry positive charge. This is the reason. So the next example here, which is more stable among these four given objective types questions. So on the base of hyperconjugation, we need the hyperconjugation is possible when there is alpha carbon with alpha hydrogen is there. When the number of alpha hydrogen atom increases, stability also increases. So we will use that principle here. This is an ethene. How many alpha hydrogen atom is there? 0 alpha hydrogen. And in this case, this is alpha carbon. So 3 alpha hydrogen is there, right? And in this case, this is the functional group. And this is alpha carbon and this is alpha carbon. 3 plus 3, 6 alpha hydrogen is there. And this is the functional group. And this is alpha carbon. And 2 alpha hydrogen is there. Right? So the order of stability will be, so the C greater than B greater than D greater than A, right? This is the order of stability. Or this is the order of stability, and which is more stable? That is the question. Which is more stable? So more stable is the C is the answer because which carrying 6 alpha hydrogen atoms, hence 6 hyperconjugative structure is there, which is more stable. Let's discuss the last question. Write the order of heat of hydrogenation in the given 4 cases. What is heat of hydrogenation? It is nothing but it is the enthalpy or energy or the heat generated when an unsaturated compound is reduced to saturated compound in the presence of hydrogen gas and a metal catalyst. So, what is the effect of hyperconjugation on heat of hydrogenation? Because when the stability of unsaturated compound is increases, heat of hydrogenation decreases. How? If the unsaturated compound or alkene is having hyperconjugative structures or the number of alpha hydrogen atoms increases, hyperconjugative structure also increases, stability increases. When the stability is more, the heat of hydrogenation is very less. So we must know the important point, that is when the number of alpha hydrogen atom increases, the number of hyperconjugative structure also increases, which increases the stability, but heat of hydrogenation, heat of hydrogenation decreases. Okay, this is the principle we are going to apply here. Let's consider the first case. In the case of a compound number A, for stability, two reasons we must consider. First is for stability, number of alpha hydrogen plus whether conjugation is exist or not. Whether conjugation is not there, conjugation means alternating single and double bond. If conjugation is not there, stability also reduced. So in the first case, this is a double bond, single bond, again single bond and double bond. So a lack of conjugation is there. So we can write it as no conjugation, right? No conjugation is here. But alpha, when we consider hyperconjugation, here alpha carbon is there. This is an alpha carbon and this is also alpha carbon. So here is C and H. Here is C and H2, CH. So 1, 2, 3. 3 alpha carbon. 3 alpha hydrogens and 2 alpha carbon. Right? 3 alpha hydrogen in the case of compound number A. But no conjugation. When we consider the second compound B, here also double bond, single bond and double bond. So here also no conjugation. No conjugation. No conjugation. But this is an alpha carbon. This is an alpha carbon. This is also an alpha carbon. So here CH2. Here also CH2. Here it is CH3. So 3 plus 2, 5 plus 2, 7. 7 alpha hydrogen atoms. Right? 7 alpha hydrogen atoms, but no conjugation. Among these A and B, B possess greater stability. Why? Because the number of alpha hydrogen atoms is more in the case of B. So we move on to the second part. In the case of C, conjugation is there. So stability is always high. Conjugation is there. Now we will count the number of alpha hydrogen atoms. So double bond, single bond and double bond. Conjugation is there. Conjugation. Now the number of alpha carbon 1, 2, 3 and 4. 4 alpha carbons are there. Here it is CH3, CH2, CH2 and CH3. 3 plus 3 6 plus 4 10 alpha hydrogen atoms. Right? Here conjugation is there. Double bond, single bond and double bond. So conjugation is possible in this structure also. And now we will count the number of alpha carbon. This is alpha carbon and this is also alpha carbon. And this is CH and this is CH. So only 2 alpha hydrogen atoms. Among these two, which possess more stability? C possesses more stability. Now we will consider the all together. Where there is in a compound, in an unsaturated compound, where there is conjugation present, which is more stable, which is more predominant than alpha hydrogen atom, the presence of alpha hydrogen atom. Let me repeat. In an unsaturated compound, where there is conjugation present, then that the stability of that compound is more than that of when we consider alpha hydrogen atom. So among these two, C possesses conjugation with the maximum number of alpha hydrogen atom. So stability order will be C possesses more stable and then D, because conjugation is there. Instead of comparing the number of alpha hydrogen atom, which compound is possessing conjugation which is more stable? So C greater than D, which indice greater than B, which indice greater than A, right? So if this is the order of stability, then what is the order of heat of hydrogenation? Heat of hydrogenation will become the reverse order. A greater than B greater than B greater than C, right? So this is the answer to the question. So heat of hydrogenation is always reversely proportional to the hyperconjugation. Means hyperconjugation is always decreases the heat of hydrogenation. Thank you.